Today, let us understand how reflection takes place in a convex mirror. So, let's get started. First of all, let us see how a convex mirror looks, right? So you can see here, it is curved outwards, all right? Now let us understand the reflection by a convex mirror with the help of a ray diagram. So, for a convex mirror, let us consider some rays parallel to the principal axis. So these rays are incident on the convex mirror. They get reflected, right? Now, this ray is along the radius of curvature. Any ray which is incident along the radius of curvature, after reflection, it retraces the path. So if we observe these reflected rays, it appears as if they are coming from a point behind the mirror, right? So we get a virtual image at this point. And that point on the principal axis is called the principal focus of the convex mirror, represented by F. So these are normal to the surface at those points, right? Therefore, this is center of curvature. Hence, which will be the angle of incidence? This will be the angle of incidence, because this is the normal, this is the incident ray, and this is the angle of incidence. Angle of reflection is this, correct? So both will be equal. If angle of incidence is theta, angle of reflection is also theta. Hence, you can see this angle will be also theta. Therefore, this angle will be how much? 2 theta. Okay? The distance between the pole and the focus of the convex mirror, which is the pole, this is the pole, and the focus of the convex mirror. So this distance, what we call, that distance is called the focal length of the mirror, and that is denoted by small f. All right? Let us consider now two positions of the object for studying the image formed by a convex mirror. Right? When the object is at infinity, that is the first position, and the second position is when the object is at finite distance from the mirror. Right? With the help of ray diagram, we'll understand the formation of image by a convex mirror for both these positions. All right? So first position, when the object is at infinity. Let us consider a convex mirror. This is the pole. Let us consider 3 rays which are incident on the convex mirror. So they'll get reflected, right? If we observe these reflected rays, they appear to come from a point on the principal axis, right? So hence, the image of an object which is at infinite distance is formed at the focus, right, of the convex mirror, right? Let us now consider the second position, when the object is at finite distance from the mirror, that is between some infinite distance and the pole, right? So let us consider this convex mirror. This is the pole, and let me consider an object which is at some distance from the convex mirror. So let us consider these 2 rays. when they are incident on the mirror, they get reflected, right? Now, this is the normal to the mirror at this point. This is the center of curvature of this convex mirror. Now you can see this ray is along the radius of curvature, hence it retraces its path after reflection. And this is another reflected ray. Of course, this is also along the radius of curvature, so therefore it retraces its path. If you observe these rays, they appear to come from an object behind the mirror. That is the image. So image is formed at this position, right? So this is the image. Here you can see as the object comes from infinity towards the mirror, the image travels from focus towards the mirror, right? As you come closer to the mirror, the image is also coming closer to the mirror. Okay. Next, you can see that the image formed by the mirror is virtual, correct? Next, the image is erect. And also you can see the image is diminished, correct? It is not enlarged, it is diminished image. Alright, so as you come towards the mirror, the image comes towards the mirror and also it is erect, virtual and diminished. Alright, so now let us see an activity which we performed earlier with a spoon. We considered the spoon and we considered the surface which was curved outwards, and we used a doll as a object, right? So let us perform that activity by using a convex mirror. Okay, let's see this. In this activity you can see the object. We have used a doll as a object. So as we take it away from a convex mirror, you can see that the image, right, is going away, and also the image is diminished. Now if you take it very far, the image will be formed at focus. You can see the image is diminished, right? Now as I bring the doll closer to the mirror, you can see that the image is erect, virtual, and it is diminished. Alright, also the image comes closer to the mirror. As the object comes closer, image is also traveling closer to the mirror. You can see that the image here is diminished image. Alright. Okay. I'm sure you must have enjoyed this activity, right? Now, let us see if I consider a spherical mirror, maybe concave or convex, and draw a line from the mirror to the center of curvature, right? Then that line is along the radius of curvature. So we see that radius of curvature is normal, that is perpendicular to the spherical surface at the given point. So this radius of curvature is normal to the mirror at this point, correct? This radius of curvature is normal to the mirror at this point. So radius of curvature is always normal, that is perpendicular to the mirror at the given point. Correct? Okay. So let us see a mirror named MN. Now, what is this distance MN? This distance, the diameter of the reflecting mirror as the aperture of the mirror. So, MN in this case is called the aperture of the mirror. All right. So, we choose small apertures, that is, it should be much smaller than the radius of curvature of that mirror. So you can see here, if this is the mirror, this is a convex mirror. So this distance is the aperture. All right. Similarly, for a concave mirror, this distance is the aperture. All right. In our discussion throughout, we shall consider only such spherical mirrors whose aperture is much smaller than its radius of curvature. Here, Mn is the aperture, and we will consider such mirrors whose aperture is smaller than the radius of curvature. All right? Okay. By considering these mirrors with small aperture, we can state the relationship between the radius of curvature r and the focal length f of the spherical mirror. So we know that the radius of curvature is found to be equal to twice the focal length. All right? So r is equal to 2f. Therefore, f will be equal to r by 2. This implies that the principal focus of a spherical mirror lies midway between the pole and the center of curvature. All right? Before we end this session, let us see a beautiful experiment using laser beam and see how the rays incident on a convex mirror get reflected. All right, so let's enjoy it. In this experiment, you can see a convex mirror and two laser beams. I've taken one green laser beam and one red one. All right, you can see here when the rays are incident on the mirror, they get reflected and they are not converging, they are diverging. So let's watch it. You can see the rays get reflected and they are diverging. The beams are not earlier for a concave mirror, the beams were converging. If you trace those diverged beams, they will appear to come from a point behind the mirror, which we call a focus. Isn't it beautiful?